Alright, what we want to do now is we want to review phase changes and just kind of give a definition to each different type of process and kind of just talk about them for just a minute. So the first, when we're thinking of our phase diagrams, and we said that the first one we can go through right here is we can either turn a solid to a liquid, or we can turn a liquid back to a solid. Now, when we're going from the solid to the liquid, of course, we define solid to liquid, that's the melt. And then, of course, liquid to a solid, we call that freezing. And essentially what happens is we're just either, when we're melting, as we've talked about in some other videos, you're just going in and adding energy, molecular motion to the little atoms, and it enables them to, they get enough energy and they kind of break free of their locked positions in the solid, and they're able to start wiggling around and moving around a little bit in the liquid state. Now, if you're thinking of freezing, what you're really doing is you're removing the energy and you're eventually locking those atoms back into their little positions, and then you become the solid state. So melting and freezing, it just depends on which way you go across that phase transition. And in the one, you're breaking apart some of the bonds that hold them in place to go from solid to liquid, and liquid to solid, you're taking the energy away and locking them into position. Now the other one up there is either you're going to go from the liquid to the gas, or you're going to go from a gas to a liquid. Now the liquid to the gas, the one that everyone's very familiar with, that's called a boil. And the one where you go from gas to liquid, that's a condensation. Now, it turns out though, you can also do a liquid to a gas below the magic temperature. So for example, if you've ever noticed, you can have a glass of water out on a table and you have some water in it. Or let's say you have an open water bottle. Leave it sit out for a week and you'll come back and your water level, or even just a day or two, and you come back and the water level has gone down. Well, that's a special form of liquid to gas phase transition. That special case in our glass is called evaporation. And so, evaporation is a special condition of boiling, or boiling is like a special condition of evaporation. And so we're going to look at this just for a minute, and then we'll talk about condensation. So, let's talk about evaporation and boiling. So what's the difference between evaporation and boiling? So, boiling occurs at whatever the vapor pressure. Boiling is when you're actually taking the water, and beneath the surface of the water, you're trying to form gas bubbles below the surface of the water that then rise out and escape into the atmosphere. So boiling, the water turns into a gas phase, right? The bubbles form at the bottom of your pot, and then they start to rise up and go to the top. Well, what happens is, if there's based on the pressure, so we said that there's pressure from the atmosphere on top of the water. And if the pressure from the atmosphere on top of the water is too high, the pressure then on the bubble collapses the bubble back in, and the bubble becomes no more because there's too much pressure. So what you need is the water has to be at the boiling point. Then the bubbles form and they go to the surface and they escape out. So the idea is that you need to have the reason the boiling point's important, and for water at sea level it's 100 degrees C, But if you're below 100 degrees C, you don't boil the water because the pressure from the atmosphere is large enough to collapse the bubbles and push them back down. But if you're at 100 degrees C, the water can boil, the bubbles can escape. So there must be some link between the pressure and the boiling point and allowing these bubbles to escape. And so it turns out is, as the pressure on the surface goes up, so as you're boiling, as the pressure, the atmospheric pressure, as the pressure goes up, the boiling point goes up. And as the pressure goes down, the boiling point goes down as well. And that's because as the pressure decreases on the surface, it's easier for those bubbles to form under the water and escape. And that's why, like, you know, if you've ever looked at cooking packages, and some of them will say, oh, at high altitudes, you know, you need to boil this longer, or you need to boil, you know, you have to change the cooking times, because at 100 degrees, the water has so much energy to impart into the food. But if the water is boiling at 95 degrees because the pressure is lowered, then you need to cook it longer to add that right amount of energy to your food. Now, as the pressure goes up, there's more pressure onto the surface. The water will boil higher, the liquid will boil higher because it needs more energy to break off and to push up against that atmospheric pressure. So boiling is just forming these gas bubbles and getting the water into the gas state below the surface, and then it escapes out into the atmosphere. So that's what boiling is about. Now, the next case is the evaporation. And what's evaporation? So evaporation is when the little guy's right there at the surface, they're kind of, the water molecules are all moving around, and so they're all just kind of, you know, they're all just flying around in the liquid. And every now and then, these guys underneath will strike the guy at the top, some of these guys on the top. And if he gets hit enough times, these guys, as they're colliding with these guys at the top, every time there's a collision, if a couple of them hit this guy, they may give him just enough energy to escape. And once this guy goes into the gas form and he flies away, he isn't coming back. As soon as he makes it into the gas state, he flies away and he's at like the other side of the room in no time flat, and he's never coming back. But what happens? As all these collisions keep happening, slowly over time, the water continues to lose these guys. More and more of these guys keep getting collided, going into the gas state and leaving and never coming back. And the idea is then that over time you just slowly lose your water to evaporation. So evaporation is when these guys, the molecules here, they collide with the guys near the surface, give them a little kick of energy. That's enough energy then that they can escape and get knocked up into the gas phase, and then they fly away and never come back. So evaporation is when you, and this can occur, of course, below, this is evaporation, and this can occur below the boiling point. Now, of course, evaporation occurs below the boiling point. Now, the part to remember, though, is if the water is near to the boiling point, this evaporation occurs faster because these guys are already highly energetic to begin with. But that's the idea of evaporation. It's kind of kicking these molecules into gas phase. It occurs at the surface, and it can occur below the boiling point. It occurs below the boiling point at the surface. And so this is the idea of evaporation. Now the last one we want to look at for these is condensation. So the idea of condensation, which you've probably all seen, is if you had some container And it's possible every now and then that a loose gas molecule will collide into here. He'll go back, he'll collide with the liquid and rejoin his brethren in the bottle or in the can or the open glass. But usually what occurs is the rate of these coming back versus going out is much drastic, depending on the temperatures. Now probably the place you've seen evaporation the most is if you've ever had, let's say you have some kind of badly drawn soda bottle. Some type of soda bottle or something. And when this is really cold, so let's say you pull a cold soda out of the cooler, what happens is the air around it, this is cold, and the air molecules strike this, and they deposit their energy. So you have the air molecule, it deposits the energy, and then these guys are all striking this, depositing their energy into the soda, and the water's condensing on there and depositing its energy into the soda. So when these collisions occur, the moisture gets the air around, gives off its energy, deposits the energy into the soda. The moisture forms on the soda, and then the soda heats up. So that's what's occurring. Like a good example of that condensation is when you get that moisture, that sweat on a cold can of soda or a cold bottle of soda, is because the air around it is hitting, turning into the water phase and putting its heat or its energy as it's cooling. As this air is cooling, it's dumping its heat into the soda and heating up your soda. So condensation is the enemy of soda. Wherever you have condensation, that means something is being heated up. And evaporation, of course, which I didn't mention, evaporation is a cooling process. Wherever you have something evaporating, something's getting a little cooler. So the idea is that you have your cold soda, as the water condenses on, it's depositing its energy and heating it up. Now, of course, this brings you to the idea of that whenever it's like really, really muggy out, what's really happening to you? So like when you're outside and you're all sad because it's muggy, the air is condensing onto you, heating you up faster than you can sweat or evaporate away your heat. So you evaporate, the sweat evaporates off you to cool down, the muggy air condenses on you and heats you back up. And so when it's really muggy out, you're miserable because the condensation's occurring on you faster than your body's evaporating out. Now, the thing we need, there's two cases we didn't talk about, two mystery cases. So the first mystery case we need to talk about is you can go directly from the solid to the gas. And you can go directly from gas to the solid. When you go directly from solid to gas, that's called sublimation. And it doesn't occur very often. Iodine is one thing that will sublimate, but there's things that go directly from solid to gas. Another thing that does this, it's the cool party trick at Halloween, CO2. You have frozen CO2, you put it in your drinks and it's bubbly and like, ooh, magic. But what it is it's the solid CO2 that you throw into the liquid. It goes directly from solid to gas phase, and that's why you can put it in your liquids without altering you can use it to cool the liquids at Halloween without altering the flavor of the beverage. Going from gas to solid, that's called deposition. And this is more of like a chemistry physics thing, but when something goes right from the gas to the solid, you're basically turning a gaseous molecule right into a solid. They use this to build, for a long time this was very popular but for building like semiconductors and trying to build superconducting materials, because you can come in at the atomic level and lay layers of atoms at a time and build up your material at the atomic level, layer by layer. So these are kind of our different processes. We can go solid to liquid, liquid to solid. which was melting and freezing. We have liquid to gas, which could be done through evaporation, or if you're at the magic temperature, you could boil. We can go gas to liquid, which is condensing. So evaporation cools us because we're going from liquid, the heat is escaping um, and taking heat off of us. Condensation is when the gas cools back down onto us and deposits heat into us. We have sublimation, which is solid to gas, which is like the frozen CO2, keeping your Halloween stuff cool and bubbly. And then we can go gas to solid, which is called deposition, which is the case is how they make semiconductors and make superconducting materials.